Hi, my name is Branson Wiens, and I did the project with Deon on week 16's problem about the Cobb-Douglas model in relation to Coca-Cola production. So the discussion problem gave us an equation that represents the production output at different levels of spending on both capital and labor, which was P labor, comma capital equals 0.02506 labor expenditure to the 0.0481 power, and then capital spending to the 0.9519 power. Now, it asks us to analyze what this means and how the moving parts affect production. The equation shows us the weight each expenditure has on the end production value and its exponent. For example, capital expenditure has a much higher weight with an exponent of 0.95 than labor does with an exponent of 0.0481. Now, the background on the Cobb-Douglas model. It was developed in 1927 in order to better estimate output in relation to labor spending and capital spending. It has been tested time and time again and proven to be a very accurate way to estimate production output, even in the modern era, and it has withstood much of the criticism thrown its way for being too stationary or rigid due to its assumption of constancy over time. So in question 1, it asks, according to the model, would it be better to spend 800 million on capital and 200 million on labor, or 700 million on capital and 300 million on labor, and then explain. And so then for this problem, you just plug in the values, 200 million and 800 million, and then 300 million and 700 million into the equation. And for 200 million and 800 million, you end up with a value of 18.8 billion cases of soda. And then for 300 million, 700 million, you end up with a value of 16.6 billion cases of soda. So we then find that having a labor expenditure of 200 million and a capital expenditure of 800 million is the better way to go, because you gain more total production from this route, given that you are spending the same amount, $1 billion. Question 2 asks us to find and interpret the meaning of P derivative L, derivative of labor, at 200 million in labor spending and 800 million in capital spending in the context of the problem. So the first step to finding the answer is to find the partial derivative of L, which you can see in the steps on the right side of the screen. So we can see that we find the derivative of the equation, and this is the answer, and then these are the steps we use to get there. So we treat y as a constant, and then we take the constant out, and by doing this we get this equation, and then we have to apply the power rule, and then once we apply the power rule, we're left with an equation that we then simplify to get our answer down here. So that's the answer you see there for the production derivative of labor. And after finding the first partial derivative of labor, then you plug in 200 million and 800 million into the equation, and you get 0.0045 billion cases of soda. So what this number means is that if labor expenditure is increased 200 million and is spent at 200 million and capital is spent at 800 million, then an increase of 0.0045 billion cases are made for each additional unit added to labor expenditure. So that in question 3, it asks us to find and interpret the meaning of production as a derivative of capital expenditure at the point 200 million, 800 million in the context of the problem. So again, the first step here is to find the partial derivative of capital. So we plug it in, and we treat x as the constant this time, and then we take the constant out. And then as we go through, we get this equation. We then apply the power rule to it, and we get this equation, which we then simplify to our ending equation, which is the production derivative of capital expenditure. So then we plug in 200 million and 800 million into our problem, and we get the number 0.0223 billion cases of soda. So this answer explains that if the labor fund is 200 million in in expenditure, and the capital fund is 800 million in expenditure, then an increase of 0.0223 billion cases are made for each additional unit added to capital. So what this tells us is, going back to question 2, is exactly what I said at the beginning, which is that capital expenditure has a much higher weight than labor expenditure does because of the added production benefit here. So then in question 4, we are asked, we now wish to generalize the behavior of P with respect to L while holding capital expenditure constant. Suppose we hold C equals 800 to be constant. Find P derivative L at L and then 800 million in capital expenditure, and then graph it versus L and describe what happens as L increases. So this is the graph that Deon and I came up with. And this graph of the derivative shows a diminishing rate of return on additional funding on labor expenditure. And it ends up approaching 0 at the end of the graph, way out here past where we can see. Meaning that eventually it will not be feasible or cost effective to continue to increase spending on labor. This graph is the result of graphing the equation which keeps capital expenditure constant at 800 million. And out here it approaches 0. So then in question 5, it says we now wish to generalize the behavior of production with respect to capital expenditure. We're holding labor expenditure constant. Suppose we hold C equals 200 to be constant, and then find production capital derivative 200 comma capital expenditure, and then graph it versus C and describe what happens as L increases. And so this graph of the derivative shows a leveling off on additional funding on capital expenditure, but it does level off at a constant gain. This graph is the result of graphing the equation and keeping labor expenditure constant. So again, this is more feasible because it does not approach 0. You end up with the same rate, constant, just about constant increase as you continue along. So in 6, make a general conclusion about the effects of increasing labor expenditure and capital expenditure for the Coca-Cola company. So we said that increasing the labor expenditure will give the company a big jump of how fast they are creating the cases, but slowly will come to a steady end. If the capital increases, it slowly keeps increasing the amount of cases being made. Increasing the capital is the better way to go. So with labor, as I said, as you go along, it approaches 0. So at a certain point, as you can see here, it's very effective to spend on labor in this region, and then it gets less and less and less effective as you continue along until it just isn't effective at all to spend on labor. Whereas capital, you're always seeing a steady increase of 0.0223 billion cases of soda for each additional unit. And that's our presentation. So again, this was Branson, Wiens, and Deon Vo, and this is our Week 16 Cobb-Douglas Coca-Cola problem.